Let's see if we can find a way to calculate the square root of a matrix. By a square root, what I mean is, supposing we have some matrix A, is there some way that we can find a matrix B so that B squared is equal to A? Well, it's kind of hard to answer this question in general. In fact, it's impossible to answer this question in general, but what we could do is add some conditions on A to sort of make it at least plausible that we could come up with a square root. And one assumption we might add to the mix here is to assume that A is diagonalizable. So let's suppose that A is diagonalizable. In that case, we can write A as some invertible matrix P times a diagonal matrix D times P inverse. And D is, the diagonal matrix just has the eigenvalues of A on its diagonal. Well, the eigenvalues are sort of telling you, in the directions where A has eigenvectors, the eigenvalues tell you how A stretches those eigenvectors. So if we're looking for a square root, something that when squared gives you A, I guess to make the stretching that A is doing into two steps, we should maybe take the square root of these guys. So, it seems like maybe a good guess would be to take the same matrices P and P inverse, but instead of having the eigenvalues down the diagonal, take the square root of the eigenvalues down the diagonal, like this. Now, for this to be possible, these numbers, these lambdas, are going to have to be positive because otherwise their square roots are complex. And, complex valued matrices are a thing. So, you could come up with square roots for if the eigenvalues happen to be negative with complex entries, but we won't go there right now. So if we let's optimistically call this B, and let's see what happens when we square B. So B is P, let's call this new matrix, instead of calling it D, let's call it E. And just remember that E squared is D. Okay. So if we do B squared, that's P times E times P inverse. So there's the first copy of B. And then the next copy of B is times P times E times P inverse, like this. But now look, we have these P's in the middle, so those just give us the identity. Now we have P times E, the identity, which we don't need to write down, times E again, times P inverse. But this is P times E squared times P inverse. But that's, E squared is D times P inverse, but this is A. Okay, so you can see if we have a diagonalizable matrix with positive eigenvalues, then we can always find a square root just by replacing the diagonal matrix of eigenvalues with the diagonal matrix of the square roots. So let's actually see how this works out in an example. So let's find the square root of this matrix here. Now fortunately, I have sort of pre-computed all of the eigenvalues. The eigenvalues for this matrix are 4 and 9. And since they're distinct, they're going to have the eigenvectors that go with these eigenvalues are going to have to form a basis for R2. And it turns out that 1, 3, and 1, 2 are both eigenvectors for this matrix, or for these eigenvalues. So let's calculate P. So we need the square root of D, right? So D is 4, 9. And taking the square roots of the diagonal entries, we get 2 and 3. And now there's actually a choice here because right, we could have taken different square roots. We could have had a -2 here, or we could have had a -3, or we could have had a negative in both places. So that, there are different choices you can make with a square root, but that's not a surprise because that's true even for real numbers, right? Every positive real number has two distinct square roots. So you can see, since we have two places to put square roots, we have two choices in each place, and there are two choices, so we're going to get at least 4 square roots, 4 square root matrices that we could write down. It's possible that there are more, I should mention, but there are at least 4. Okay, so our matrix P in this case is going to be 1, 3, 1, 2. P inverse is -2, 1, 3, -1. Okay, so now we can form our square root matrix. That's going to be P times our square root of D times P inverse. So 1, 3, 1, 2 times 2 and 3 down the diagonal times -2, 3, 1, -1. Okay, so now we just need to multiply all of these out. So the product on the left, we're going to get 2, 6, and then 3, 6 times -2, 3, 1, -1. And then let's see, so -4 plus 9, that's 5, and -12 plus 18, that's 6. And over here we got -1 and 0. Okay, so this is supposedly our square root matrix. Of course, the proof of the pudding is in the eating, so let's square it and see if we get back to our original matrix. So multiplying this matrix by itself, we get, let's see, 25 minus 6, so 19, and then 30, and then up here we got -5 and 6. Sorry, -5 and -6. With any luck, that's what we started with. 19, 30, -5, -6. It worked. So you can see that if you have a diagonalizable matrix, it actually, what the diagonizability lets you do is turn a lot of questions about matrices into questions about just the diagonal matrix that contains the eigenvalues for the matrix. Of course, for this to work, right, the reason you need diagonalizability is if you don't have diagonalizability, there's no way to get a matrix with the right entries down the diagonals so that you can work just on the diagonal entries. For another example in this theme, let's think about matrix exponential. What would it mean to define e to the a for a matrix A? Can we use a matrix as an exponent on an exponential? Well, there are a couple ways to think about this. And one way is to think about it in terms of diagonalization. So if A is diagonalizable, so A is P times the square matrix with its eigenvalues lambda 1 to lambda n down the diagonal, then you might think, well, the thing to use for this matrix exponential would be P times e to the lambda 1 down to e to the lambda n times P inverse. Okay. So how can we tell if this is a good definition? Well, what is it that makes the exponential? One way of looking at it is it's the power series. It's the power series for the exponential that makes it what it is. And the power series for the exponential is the sum from k equals 0 to infinity of 1 over k factorial times x to the k. Right? This is what makes the matrix exponential make sense. So what we could do is see if this definition matches the power series for e to the a. So I guess what we'll have to do is plug a in for x into this expression. So let's do that. Sum from k equals 0 to infinity of 1 over k factorial x to the, plugging in a to the k. So, but a is p times our diagonal matrix. This right here is what I'm calling D, our diagonal matrix, times p inverse, okay, to the k. Now the thing about this product, p times d times p inverse to the k, is that as long as k is bigger than 1, we can write this as p times d times p inverse p times d times p inverse times right, there's going to be, so this is the first factor of p times d times p inverse, and then there, as long as k is bigger than 1, there's another factor right over here, right, like this. And you can see that whenever we have two factors next to each other, the p inverse and the p are going to multiply to give us the identity, and so they disappear. And then we get a d times a d, but d times d is d squared. Right? And the thing about d times d being d squared, that's actually easy to calculate, right? Because d is diagonal. So whenever we multiply a product like this, the p inverses and the p's in the middle all cancel, and what we get is, let me just write it down here, what we get is 1 over k factorial times p times d to the k times p inverse. Okay. All right. Because all the p's and all the p inverses and p's that are interior in this big product all are canceling in pairs like this. Okay. But look, now that we have just one copy of p and one copy of p inverse, we can actually move them outside of this sum. So the p on the left we can factor out to the left, and the p on the right we can factor out to the right, like this. And the stuff in the middle is the sum from k equals 1 to infinity of 1 over k factorial times d to the k. And, you know, this is the matrix in parentheses up here. This is just the sum from k equals 1 to infinity of 1 over k factorial times lambda 1, and then same down the diagonal to the last one, which is sum from k equals 1 to infinity of 1 over k factorial times lambda n. But this is this is exactly what we suggested should be the exponential, right? That's right here. So we made a good guess for what the exponential should be. Right? Each of these, I guess, each of these power series is e to that eigenvalue, like so. Okay, so the reason that this works is because power series, because power series are put together with multiplication and addition, we can factor out these matrices P and P inverse, and then also this matrix product D and the sum and the scalar product here sort of happen component-wise, specifically because D is diagonal, right? That's really what's making this whole thing work. Now, I should mention that, in fact, this power series here actually makes sense for any matrix, not just any square matrix, not just diagonalizable matrices. But showing that it works for any matrix is actually kind of difficult because, right, if you put any old matrix in here that doesn't necessarily have to be diagonalizable, it takes a fair amount of work to show that no matter what matrix you start with, the powers, right, when you raise a matrix to larger and larger powers, in general, what's going to happen is in the resulting product, the entries get bigger and bigger and bigger. So what you have to show is in this matrix product, the entries, once you divide them by 1 over k, they sort of settle down. They don't remain so large that this sum becomes undefined. So it's actually possible to define the matrix exponential in general, but it's tricky, except for this diagonalizable matrix case. For diagonalizable matrices, it's pretty straightforward to define a matrix exponential.